Hello guys, welcome to another tutorial series on EMV. Don't forget to smash that subscribe and like buttons if you like and appreciate my videos. I will be talking about the transmission protocol T1, the block-based protocol. My last video was about the T0 protocol, which is a character-based protocol. Check it out to better understand this video if you haven't done so yet. I will briefly talk about some of the unique characteristics. The difference with the T0 protocol from my previous video will be highlighted on each characteristics. Next, we will take a look at the block structure used. Thereafter, I will show you the different block types and then give a brief explanation of their usages. Finally, I will of course present the protocol in a demo using the hardware setup I presented in one of my videos. Let's do this. Here the points in green are for the T1 protocol while the black are for T0. As opposed to T0, the T1 protocol is a master-master protocol. Both the interface device and the IC card can trigger a command. So the most obvious advantage of T1 protocol is the ability to manage data flow in both directions. T1 transmit blocks, which are a string of characters, while T0 transmit characters. No prior knowledge of process bytes are required for T1 protocol, and it makes it easier to transform a large amount of data through the so-called chaining from a single command trigger, but the implementation is much more complex as compared to T0. Error handling is also easier because each block must always have a checksum byte, which is the exclusive of all the characters in the block, and any erroneous block will have to be reset. At the end, T1 has a lot of improvements on T0, which is why T1 was specified, but the price for that is a more complicated specification to implement. The block structure is also very simple to understand and implement. It is made up of three main fields, one of which is optional. Depending on the type of block and command to be used. The first field is the prologue field, which is mandatory. It is 3 bytes long and consists of three components: node address, the protocol control byte, and the length, each of which is a byte long. The node address is to code the address of the source and destination node of the block during a transaction. For the ISO 7816, it is not fully used and always have to be 0. Any block sent or received with a node address different from 0 will be considered invalid. The second component in the prologue field is the protocol control byte, which is used to code control information like block type, block number, etc. The third component is the length, which codes the amount of bytes to be located in the next field, which is the information field. And that is why it is optional, because it can also be empty depending on the use case. But it is exactly where our commands and responses will always land. Check the video on commands and response to learn the basics if you haven't done so yet. The last field is the epilogue, which is the error detection field. It contains the error detection byte, which is the exclusive of all the bytes in the block. There are three different types of block. Information block, or the I block, which is used to convey APDU. APDU are application protocol data units. This is a block type used for payment transaction with cards that support the T1 protocol. The second block is the receive ready block, or the R block, which is used to convey acknowledgements. And the third block is the supervisor block, or the S block. It's used to exchange control information. Since the I block is the only block I use in my implementation for now, I will just explain how it is coded. If you have any case where you will have to use any other block types, just put a comment below and I will reply. The first 5 least significant bits are reserved for future use. Bit 6 is used when a blockchain is to be used. To explain the blockchaining, I will have to refer you back to the answer to research video I did. Check it out if you haven't done so yet. The answer to research contains a byte, the TA3 byte, which codes the maximum block size in the range between 16 and 254 bytes a card can receive if it supports T1 protocol. So this value will define if you have to use chaining or not. Okay, let's jump into the live demo. Welcome to the demo session. I've inserted my card in the card slot that supports the T1 protocol. So as you can see, I've let it run, and here I'm about to select my PSE. Here I've set up my um, node address, my PCB, and my TXLAN, and then the command which I have to send the APU in this array here. And I sent it, and then I received the response from the IC card. So in this case, my PCB is 0, so it is an I block. There is no chaining, and the sequence is 0, the first sequence. So normally whenever you send a block to the IC card, you have to always toggle the sequence bit. If it is a case of a repetition, then you have to let the sequence bit remain the same as the previous block. Okay, yeah, this function here is the one that sends my block. And like I said, there is also this byte value from the answer to research, which that is a TA3 byte, which I store in this variable here. It's the FE, so it's the maximum. And here I check if my command length is greater than the maximum length. If it's the case, then I have to strip my block into smaller blocks and send them through chaining. So that is the idea of block chaining. So in this case, it's definitely no block chaining and it goes easier. So I've sent it, and then I received 3C hex of block into my receive buffer. And I also told you that the IC card first sends back your request. So all this one here from 0 right down to DD is the request. So DD is the EDC, the checksum, error checksum, and the rest is my response. So that works perfectly right up to this point. These are my status byte 9000, and this one is my EDC byte. So perfect. Okay, so to simulate blockchaining, what I've done now is similar to my example. I've changed my transmission length to be 5 bytes only, and then I set my chaining bit in my PCB here, and then I let it run. So what my IC card sent is not similar to what it sent before, because this one I instructed my IC card that this is a chaining and this is the first block. So the IC card now I let it run and then receive the reply, and then if you can see here, I sent this is the NAT, this is the PCB, which is saying that it's a chaining, and I send the length, which is 5, and I send 1, 2, 3, 4, 5 bytes, and I send the ECD. What the IC card sent back is a NAT, there's a node address of 0, and then 90. 90 is an error block instructing me that I should send the next sequence. So that is an error block with no errors. That is this block. So with a sequence of 1. So my IC card is instructing me to send back to send the next sequence of my block. And yeah, that is just how chaining goes. So I will send the sequence until when I send the last block, then the IC card will send my response, which will definitely look like what I had when I was not doing a block chaining. So that is just how it goes. I don't have any card that will really push me to test the chaining thoroughly, but yeah, I have implemented the case. Hopefully it's perfect. So what I did, this one I can let it run completely because it's not a perfect chaining example. I just hard coded the length here and then set the chaining bit. But if it is say for example a rechaining case, then my code will have to come in here and then detect the block that I received from the IC card. In this case, it's going to be an error block, and then I'm going to check if I set the chaining bit before sending to the error block to the IC card, and then the IC card replied, and then I have to check if the IC card wanted me to repeat my block or wants me to send the next sequence, and then I have to send the next sequence until I send in the last, and I expect the response from the IC card. So that's it for today. I hope you enjoyed it. If there are any questions, just put it in the comment section and I'll be happy to answer them. Don't forget to smash the like and the subscribe button. Yeah, I hope you enjoyed it. Thanks. Bye bye.